Hello everyone. Today we are going to talk about Network of Things. We are going to focus on the NIST special publication 800-183 titled Network of Things. We already talked about that there is no actually good definition of Internet of Things. So this document is actually helps us to see the big picture and provides a good ontology, provides basic definitions. So in the slides, I try to highlight the main points of this document, and so that we can talk about what the network of things. So all of the slides and actual text I'm going to provide is from this NIST special publication 800-183 network of things. So let's look at the big picture they draw in this document. So this picture is also taken from that document. So at the Internet of Things, we work with data. So this data mainly comes from sensors. So we have a lot of sensors in this picture. And sometimes the number is huge. So it is better to cluster them. So this is why we have clusters of sensors. And these clusters send their data to some aggregator. So these aggregators actually sometimes perform some operations like on the cloud, or maybe they have their own CPU and so on. So they gather this data, and sometimes they run codes like if-then statements, and depending on the result, they can talk to sensors back and maybe ask for more data or ask them to measure something else and so on. So we have this kind of picture. So we have sensors, we have clusters of sensors, we have communication channels. This can be wired or wireless. And we assume that these sensors are not that, do not have that much capability in terms of CPU or memory. And sometimes they are better powered, and they communicate with these aggregators. Again, we have some e-utilities here, and we have some decision triggers. So this will be the main picture this document draws. And they use the term network of things instead of Internet of Things because most of the time these networks don't have to be connected to the internet. So network of things are actually bigger than Internet of Things, let's say. So Internet of Things is just a subset of network of things. So keeping this picture in mind, this document tries to explain and expectations from these elements in the picture. So let's start with an introduction. From agriculture to manufacturing to smart homes to healthcare and beyond, there is value in having numerous sensory devices connected to larger infrastructures. So this was the main promise years ago about Internet of Things, so that we will have smart homes. Our coffees will be ready before we go to the kitchen and so on. But today we are somewhat living in that world. We are having many devices, smart devices, so our homes and cities becoming smarter and smarter. But of course, security becomes a concern at this point. This technology advance acknowledges the reality that human society is moving towards smart and smarter systems. Yes, the rapid advances in computer science, software engineering, systems engineering, networking, sensing, communication, and artificial intelligence are converging. This is actually the road that led us to the Internet of Things. And the tethering factor is data. There's no formal analytic or even descriptive set of building blocks that govern the operation, trustworthiness, and life cycle of Internet of Things. So this is actually the main problem that I mentioned at the beginning of this course. Everybody has a different definition of Internet of Things. So this is why I'm using this NIST document to agree on some definitions and expectations and so on. A composability model and vocabulary that defines principles common to most, if not all networks of things, is needed to address the question, what is the science, if any, underlying IoT? So this is why we are focusing on this special publication of NIST, again 800-183 Network of Things. So this document offers an underlying and foundational science to IoT based on a belief that IoT involves sensing, computing, communication, and actuation. So that is the main idea behind this document. Because no simple, actionable, and universal accepted definition for IoT exists, the model and vocabulary proposed here reveals underlying foundations of the IoT. For example, they expose the ingredients that can express how the IoT behaves without defining IoT. So that is the main approach of this document. This offers insights into issues specific to trust. We consider IoT to be one type of network of things. From this point on, we will refer as that NOT, and the NOT to be one type of a distributed system. So that is the main approach of this NIST document. So how the primitives are defined in this document. So let's look at how NIST sees the primitives in a network of things. So they believe that there are 5 primitives here. They are sensor, aggregator, communication channel, external utility, shortened as e-utility, and decision trigger. Rarely there may be some nodes that do not contain all of this. So sometimes you might have a small network of things, or sometimes you don't need to make a decision, but only to gather data. So you might have sensors, aggregator, but no decision trigger and so on. But most of the time, we will have all of these primitives in a network of things. So let's start with the first primitive, sensors. A sensor is an electronic utility that measures physical properties such as temperature, acceleration, weight, sound, location, presence, identity, etc. And personally, I really like sensors, and I really enjoy the fact that our mobile phones getting more sensors when the technology advances. We even have barometers that are mobile phones, so actually we can gather a lot of data with our sensors. But there are many different sensors that you can use. All sensors employ mechanical, electrical, chemical, optical, or other effects at an interface to a control process or open environment. Basic properties, assumptions, recommendations, and general statements about sensor include: sensors are physical. Some may have an internet access capability. So these are actually the sensors that we are focusing in this lecture, because we want to look at the devices that have communication, computational power, and these devices communicate with others in a wired or wireless way. So we want to measure check the security of these communications. This is why we are actually will be talking about lightweight cryptography. Sensor output is data. A sensor may also transmit device identification information, such as via radio frequency identification. Sensors may have an identity or have the identity of the thing to which they are attached. Sensors may have little or no software functionality and computing power. More advanced sensors may have software functionality and computing power. So this is one of the things we focus in this course, because we may have sensors which are very limited in capability, like they have a few bytes of memory, very non-powerful CPUs, let's say. But you can also use devices like Raspberry Pis as a sensors too. So the spectrum is really huge. Sensors may be heterogeneous from different manufacturers and collect data with varying levels of integrity. So this is also a problem when you're creating your network of things. because even if you try to buy the same device or same sensor a few years later, you will realize that the technology is advanced and the device you were using is no longer produced, but you can get something better in terms of computational power and so on. So from time to time, even if you try to build a network of things with the same devices, it may not be possible. So different devices will have different computational power, and again, they may the way they collect the data might change. So you may have varying levels of data integrity. Sensors may be associated with fixed geographic locations or mobile. They may be mobile. Sensors may provide surveillance. Cameras and microphones are sensors. So this is also important, and actually there is a huge security problem here. So with the advance of these technologies, a lot of people wanted to put cameras to their homes, their gardens, and their working places and so on. And they have most of the time Wi-Fi communication. So you can go to any place, and from your mobile phone, you can check the cameras you have put to your garden or home or workplace. But in reality, we observe that most of the time, these communications are not encrypted. Sometimes they don't have any username password protection at all, or sometimes they use default username and password. So actually you can abuse these systems and look at the cameras of a lot of people who hasn't used any password protection or any encryption at all. So this is actually currently a huge problem which people are not addressing to. Sensors may have an owner who will have control of the data their sensors collect, who is allowed to access it, and when. Again, this was actually the problem I was mentioning. Most of the time, people don't know this property, so without knowing, they allow access to everybody in the world, which actually is not a good idea in terms of the cameras and microphones, I mean. Sensors will have pedigree, geographic locations of origin, and manufacturers. Pedigree may be unknown and suspect. Sensors may be cheap, disposable, and susceptible to wear out over time. We also mentioned this because these are cost-sensitive devices. Maybe a manufacturer will probably manufacturing millions of these sensors. So sometimes they have to be cheap. This is why sometimes they don't have enough capability to run modern cryptographic algorithms. So this is why we need a lightweight cryptographic standard for these devices. There may be differentials in sensor security, safety, and reliability. For example, between consumer grade, military grade, industrial grade, etc. So this is also the thing that we are trying to address here. Most of the time, consumer grade devices don't have any encryption at all. This is why we are trying to have a lightweight standard and force all of these manufacturers to build their devices with this standard, so that even the cheap devices comes with acceptable security. Sensors may return no data, totally flawed data, partially flawed data, or correct and acceptable data. Sensors may fail completely or intermittently. They may lose sensitivity or calibration. So these are the things people have to look at in their network of things. Sensors are expected to return data in certain ranges, for example, between 1 to 100. When ranges are violated, rules may be needed on whether to turn control over to a human or machine when ignoring out-of-bounds data is inappropriate. Sensors may be disposable or serviceable in terms of calibration, sensitivity, or other forms of refresh. Complex and expensive sensors may be repaired instead of replaced. But as you can guess, today's technology actually trying to move to a place where repair instead of repairing, you go and buy a new one, which actually I do not promote, let's say. Sensors may be powered in a variety of ways, including alternating current, solar, wind, battery, or passively via radio waves. This is the reason we also need lightweight cryptography, because even if you have the computational power to run any cryptographic algorithm, if you are powered with battery, then it will be good to have a lightweight algorithm that uses less battery, right? Sensors may be acquired off the shelf or built to specification. Sensors acquire data that can be event-driven, driven by manual input, command-driven, or released at predefined times. So it depends on your choice and the type of your network of things. Sensors may have a level of data integrity ascribed. Sensors may have their data encrypted, which we in the practice see that this rarely happens. Instead of sometimes encryption, they just use hash functions and so on. Sensors should have the capability to be authenticated as genuine. This is important because if the device you are using is not genuine, then maybe it doesn't provide the capabilities that you were expecting. So actually, this is an important property that sensors should have. Sensor data may be sent and communicated to multiple nodes. A sensor may have multiple recipients of its data. Sensor data may be leased to one or more nodes. The frequency with which sensors release data impacts the data's currency and relevance. Sensors may return valid but stale data. Sensor data may be at rest for long periods of time. A sensor's precision may determine how much information is provided. Uncertainty of sensor data should be considered. So this precision is also important. Sensors may transmit data about the health of a system, such as is done in prognostics and health management. In this model, we don't classify humans as sensors. So this is important in the NIST document. So NIST don't consider humans as sensors. This is important. Again, I told you that people don't have an agreement on the definition of Internet of Things. So some people consider humans as also sensors, but NIST and so we in our course will not consider humans as sensors. Humans are classified as an external utility in this document and also in our course. They can still act in a sensor-like role by manually feeding data into a node's workflow and data flow. Humans can influence sensor performance through failure to follow policy, sensor misplacements, etc., or their positive analogs. Humans are potential contributors to sensor failures. There is a lot of examples in real life for this. Security is a concern for sensors if they or their data is tampered with, stolen, deleted, dropped, or transmitted insecurely so it can be accessed by unauthorized parties. So that is the part we are focusing. Actually, this is where the lightweight crypto comes into play. Building security into specific sensors may or may not be necessary based on overall system design. Reliability is also a concern for sensors.